Well, welcome everyone. We're going to be talking about a new feature of Simcenter Test Lab Neo, which is called Virtual Instrumentation. And this makes use of a new feature, which is this CAD display. So we're going to bring in some CAD into Test Lab. So the first question you might ask is, why would I want a CAD display in Test Lab? Well, there's really three primary reasons. First is we want to increase the efficiency and accuracy of our geometries. A lot of times we're testing products or components that our organization has already spent time and money developing a CAD model for, right? And anytime we spend duplicating that effort, making measurements, the tape measure, and we're measuring the distance between our accelerometers and our shakers and things, we're duplicating effort, and that process tends not to be very accurate. In addition, the accuracy that we will gain when we use these CAD models will enable us to do on a very high level some of these more advanced techniques, some things like component-based TPA, where we're calculating blocked forces, frequency-based substructuring, which is one of the tools underlying something like virtual prototype assembly, where we can put together virtually a system of components and then not only predict what FRFs and things are going to look like, but actually oralize and listen to those virtually assembled products. And then on a real practical level, there is some useful guidance that we can get from this virtual instrumentation tool for things like impact testing and setting up a shaker test, and I'll show you some of those as well. We'll talk a little bit about the details of how you get access to the CAD display for Simcenter Test Lab, and then I'll show you some of the features in a demonstration. So why would we want a CAD display? We have the CAD models, right? In our organization, they're very accurate. They're the latest and greatest information we have about the geometry and details of our components. And if we use that pre-existing CAD, it allows us to set up our test virtually before we even maybe have access to that component. A lot of times prototypes are getting more and more highly demanded, and so the time we have with the actual physical prototype is going to be even shorter. And so any setup I can do beforehand is going to really help me with that process. In addition, when I go to instrument the vehicle or the component in the real world and hook it up to my SCADA data acquisition system, we can use that pre-made, virtually prepared sensor geometry and use that in aiding our channel setup and making sure we're plugging in the right wires to the right inputs. All of that ends up with faster instrumentation and ideally a very highly accurate geometry. All we have to do is make sure our real world version matches what we see in CAD, and we'll have a great deal of accuracy. So as far as efficient channel setup, we can do this transducer layout and selection all ahead of time before we're in front of the prototype. And then we can graphically go around the CAD model where the transducers physically appear in their actual size and shape and things, and actually just click on it and say, I'm plugging this accelerometer on the back of this powertrain into channels 7, 8, and 9. And so having that graphical interface with a realistic looking structure error proofs that process for us. So we can do this ahead of time. We don't have to wait for the physical prototype to be available, and we can graphically relate the transducer locations to input channels. In addition, this will help us error proof transducer orientations. In this example, in the little video here, all the transducers are oriented the same way, but that may not be the case very often, right? And so this will help us error proof that by automatically extracting the correct Euler angles and things like that for us while we do this setup. And all of that will speed up our instrumentation time. So the second enabler is that highly accurate, right? That was the efficiency stuff. What about the high accuracy? We know from previous studies, the variation that you get in your measured FRF can be quite significant. In this case, these are the variances or the effects of moving the impact hammer plus or minus 2 millimeters between impacts. And so very, very small shifts in where that force is being put in or where that accelerometer is measuring the response of your structure can create big changes or differences in your frequency response functions. That's what we're trying to avoid. So a tool like virtual instrumentation allows us to very accurately communicate our intentions. I want this accelerometer to be 18.5 millimeters from this boss on this face. It allows us to not only communicate that, but then verify that we're setting up and measuring in the actual intended location. And then with the virtual instrumentation, we'll be able to utilize those actual measurement locations in a very high degree of accuracy. So advanced techniques, component-based TPA, virtual prototype assembly, etc., are going to take these FRFs that we're measuring on our structure, and they're going to do a bunch of further calculations downstream. There's matrix inversion, there's all kinds of frequency-based substructuring, and so the quality of those FRFs is more important than ever. And so this is an example of a blocked force calculation done at the actual connection location shown here in red. We see this peak in the block force at this frequency. And this is what we may have gotten in the old days where we didn't have a tool like virtual instrumentation and a CAD-based display, where we're saying, oh, we're close to that attachment location. We'll just measure our response and our impacts couple millimeters over. And what we'll see is when we go downstream and calculate something like a blocked force, we get a very significantly different answer because of that very small variance in where we're making our measurements. So something like a CAD-based geometry is going to enable us to keep that accuracy and thus the fidelity in our downstream calculations, including those Euler angles, which is something that, being from a modal background, I particularly like because I always hated Euler angles. Upfront conditioning and feedback for virtual points. So one of the other advanced techniques that we're going to use for something like component-based TPA, virtual prototype assembly, is virtual point transformation, where we actually want to measure and calculate FRFs from points that are physically unable to be tested, right? The center of this cylinder here is where we actually want the FRF to be. We obviously cannot impact the engine block in a space, in a point that's hanging out in space. And so we use a tool like virtual point transformation to calculate what the FRFs would be. And we feed that transformation a bunch of information from transducers on physically accessible locations around the structure. When you're laying something like that out, it's really important to know whether you have enough references or the inputs, the red arrows here, and enough responses, the accelerometers. Do I have enough unique locations, offsets, directions, etc., to fully define this virtual point out in space here in 6 degrees of freedom? So 3 translations and 3 rotations. And so we do that using a condition number. What you're seeing in this animation is that condition matrix, the condition number being calculated for you as I'm adding the transducers, and it's all just based on the geometrical layout of these transducers. There's no data being fed here, it's just a geometrical calculation. But knowing that up front before you've taken a piece of data that, yes, this is going to properly condition my matrix, both from a response and a reference perspective, gives me a lot of satisfaction. If I didn't see a good condition number there, I might be able to add some more measurement locations, either response or reference locations, and then improve that condition number, all again before I've taken a stitch of data. So that sort of foresight can really increase the efficiency and quality of these advanced techniques. So the CAD-based geometry, having the geometrical relationships of all these points that we're laying out baked into it, allows us to do those calculations essentially instantly. And then there's some very practical things like, hey, I want to test inside this cylinder. Am I going to be able to swing an impact hammer in there? Do I physically have the space to get a good impact in there? You can put something like a transducer. In this case, it's a PCB impact hammer. You might say, I don't like the look of that. So you can say, what if we used one of our Q source shakers? Will that fit in there? Oh yeah, that fits in there beautifully. And again, because we have the geometric data or information in the CAD model, we know, what angles all of these things are going to be tested at, because they'll always be normal to that surface, right? We mount that shaker on there, it's going to be normal to that contact point on the surface. And all of that is taken care of for us by using the CAD model. So how do we get this CAD display? Well, it is a Simcenter TestLab Neo feature only at this point. So you need a desktop Neo as a prerequisite for it. If you have TestLab Desktop Classic, you have access to Desktop Neo. They are operating off the same license. And then you need to install and get access to this CAD display license. Now, this is a free license. There's no cost for it, but you do need to sort of purchase it, so to speak, because of the way that the license is handled on the back side. So you need a zero cost quotation. You can get that from your salesperson. We then send you that license and you are able to download and install the CAD display. This is a separate installer from your TestLab install, so it's something you have to kind of do on purpose. And then once you have the desktop and that DTP0080 license, you'll build that in using geometry creation for Neo, which is GEO0203. This is analogous to the geometry add-in for Classic. And then you'll add in Simcenter TestLab Virtual Instrumentation. Now, Virtual Instrumentation itself is 40 tokens, so all of these things are tokenable outside of the desktop, and obviously not the zero cost license either. But if you add in geometry, that'll be 16 tokens, and then Virtual Instrumentation will unlock sort of the rest of the stuff that I'll show you, where we're actually putting in the accelerometers and the impact hammers and using the CAD display itself. So a total of 56 tokens for the stuff I'll show you today. When you go to download the product, obviously, in this case, you'll have the standard Simcenter TestLab.iso. This is the main TestLab product, and then you'll have a separate installer that's this CAD display. It's pretty obvious what it is, but you'll download them both. You install TestLab first, and then you will install the CAD display. And I would recommend not installing the CAD display until you get the license from us, because we're going to do some of that licensing stuff during the install so that we don't have to go back and reconfigure it after the fact. It's able to be done after the fact. It's just a little bit easier if you do it during install. Some notes on the CAD files that you'll need. They must be either .prt, which is a NX format, or a .jt file format. A CAD program like NX can be used to convert something that might be a STL to the required format. One of the neat things that I'll show you are the geometric features available in a .prt. Unfortunately, if you are converting an STL file into a .prt or a .jt, an STL file has no thing defined as a geometrical surface or element. It's just a mesh out in space. And so some of the things that I'll show you won't exactly work directly with an STL model, but most of the features will. So if you have a CAD model, either in CAD format or in STL format, we can bring it in. We just need to convert it using one of the CAD programs to one of these two formats. So with that presentation stuff out of the way, let me show you some of this in the software. So this is Simcenter TestLab Neo. And if I go up here to File and show you the add-ins, I have geometry creation loaded, so that's 16 tokens. And down here in the V's is this virtual instrumentation, that's 40 tokens. So those are the only two products I have loaded right now. And I open up desktop, it's going to look like this. If I go to, might start here on the desktop, but I go to this geometry tab down here. And this is where I'll see a typical geometry display and the XYZ coordinates and things that I would in like a TestLab Classic. I'm going to go over here to this virtual instrumentation tab, and here I've loaded this CAD model of this front right suspension for a vehicle. So you see some suspension. You see the wheel and tire assembly. I got this model by hitting this load CAD and then giving it the path to that model, and it loads up in here. And I'll give you some of the little sort of mouse tricks, if you will, or tips, as they are a little bit different between this CAD display and a typical test lab geometry display. And for example, in order to rotate it, I'm using the center sort of scroll wheel button on my mouse, whereas in a standard geometry test lab display, that's a left click and drag. And so there's some subtle differences. And if you're not used to working with CAD models, this guy down here sort of gives you an orientation idea of what you're looking at, and you can get kind of lost sometimes. So you can click on these faces and that will show you the front of the model. If I click this corner, it'll be my isometric. I can look at the right side view, etc. And I can obviously zoom in and do all kinds of good stuff. So what I'm going to do is I'm going to lay out sort of a test here, and I'm going to pretend I'm going to do a road noise block forces calculation. So I'm going to treat this wheel and tire as the source. I want to calculate some block forces where this wheel and tire interface with the rest of the vehicle, and that would be right here at the center of this spindle location. So you can see, and typically when it comes in, your model might look like this. So the first tip I have, if you have a .prt or a JT file format that started as CAD, you can use this shaded and add this shaded with edges. And that just puts, some lines around the different geometrical features of the CAD model itself. And it will allow you to do things like, if I hover over this arc right here for this center hole, you see it suggests this center location. So this is the center of this hole here. So that's the kind of stuff you get using the geometrical features inside. If this had come from a STL file, there wouldn't be any such thing as this is being an arc that has some center point. It would just be a 3D mesh of points hanging out in space. So there's no geometrical surfaces or elements to reference. But so I have this structure and I want to start adding some measurement points, right? So I'm going to come up here, I'm going to create a new component, and you see I get a new component in my geometry tree here. I'm going to rename that to say wheel. And as I start adding transducers and reference or excitation locations on here, I want it to use component naming. Okay, because I like to use that to keep track of these things. So I'm going to use component, and if I had more than one component, I would get a pull down here. And I'm going to number those. I'm going to start them from 1, and I'm going to take out this prefix. I could have a prefix if I wanted. That's where I would do it. Now I'm going to start adding some transducers. So first thing we want to do in this case is we're going to add a virtual point. So you see over here in the sensor library, I've got some accelerometers, I've got some inputs like a impact hammer, grouse microphone, our Q source shaker, and in this case, I'm going to create a virtual point, and I'm going to utilize that geometric feature and place it right here at the center of that wheel. So it's this point kind of out in space that's the direct geometric center. That's what I'm going to consider to be the connection point between my source and my receiving structures for something like component-based TPA. Now I have one spot or one node point on my geometry into the component wheel. And now I'm going to start adding some additional transducers. You can click on this guy. And as I move around my structure, you see it kind of highlight some of the structures, and I click there and it puts the accelerometer right on the face there, okay? And over here I can change something like, what if I don't want it mounted on that face? What if I want it mounted like on the X face? Let me select that first and then change that. And now I see it has rotated that transducer, so now the X face is what I mount it to, okay? And this is geometrically accurate version of this PCB model 356A32. Accurate, so much so that if I zoom in here, inside this accelerometer, there's a sensing element in here. There's a little inertial mass in here that's got the piezoelectric crystals on 3 directions, right? It's a triaxic cell, so it can measure acceleration in 3 different directions. This is accurate to the level of detail that there's a seismic mass in here at some offset, and that offset is where the acceleration will be measured for this given transducer. So it's not even just this XYZ point of this location, but that offset internal to that accelerometer is also being comprehended, again, to keep the accuracy and quality in our measurements, okay? So if I continue my little instrumentation here, I'm going to make a couple measurements, and I'll take this guy over here. So these are my responses, and this guy, let's say I'm going to put him back on the negative Z face. Okay, and I'm doing that to kind of highlight how it's going to keep track of that Euler angle for me. Now, one of the other things I can do, because I have a CAD model and I want to have as much accuracy in here as I can certainly translate this. And if I zoom in, I can grab these axes, and you see it starts giving me a dimension from how far away it is from that point. And so I can start by saying, oh, let's put it in the center of that bolt head. Let me back up a little bit here. And then I'm going to move 37 millimeters that way and 15 millimeters down from that bolt head. So now I have that transducer perfectly located on that surface, okay? Likewise, if I have a geometric feature of my structure that I want to align the transducers to, I can do something like click this axis and say align it to this feature. So this hex bolt has a straight line as a geometric feature, and I can say align all of these axes to that bolt face. And in reality, a hex bolt might be tightened a different amount, so that wouldn't necessarily be the best geometric reference, but it gives you the idea of what can be possible in terms of orienting your accelerometers and transducers with respect to features that are part of the CAD model. Now I'll add some excitations. And so I have these input forces, and I can come in here and add a bunch of these guys. I can even come on to a face like this on the side, and it automatically places those forces normal to the surface that I selected there. And there we go. And I can always, if I don't like where that guy got placed, I can come in here and I can drag him. And you see it follows that surface, so that blue axis is always orthogonal to the surface where it will be mounted. So now I've got some impacts. I've got a couple different directions. In the case of using one of our integral shakers, we even have these components like the QTRX, which is the sort of multi-plane, in-plane adapter. And so you see we've got this sort of shell device with several different mounting positions on it. And these angles are associated with these letter indices. And so if I take measurements at the L and the F faces, those angles and orientations are already baked into Simcenter Test Lab, and so it will automatically extract those angles for me, provided I've oriented the QTRX itself in some way that is reproducible. I can take this force and I can move him. So now this QTRX is now a part of my structure, and if I get that on the face and not on the letter there, it will be ideally orthogonal to the surface. It allows me to identify the reference location in multiple directions. And I can also, add things like the QTRX. Again, this doesn't really help me from a data acquisition standpoint. These excitation points are really what I use. This helps me just geometrically know, can I fit this guy in here inside where this brake caliper is? And yep, no problem. So I'll delete a couple of these guys. And then I'll show you this sort of geometric validation for something like a virtual point. So this virtual point here is what I created first. If I highlight that guy, I get this define virtual point dialog becomes selectable. And now I just go through and I select the transducers that I'm going to use in terms of, these are all response locations, and it knows, oh, that's an accelerometer, that's going to be a response, and I'm going to use those responses to condition the response matrix. So they are automatically being put in. It knows it's a triaxial accelerometer, and so it's using 3 directions for each of those points, and I get a condition number there. Okay, so I added those transducers. Again, if I didn't like this reference condition number, I could add some transducers and increase that or better that condition number. Likewise, I guess I can add my forces and it starts conditioning. So now I have 3 references. And as I increase those, because I'm trying to extract 6 degree of freedom virtual point, I need at least that many references. And so you see at 5, it's red and it will not even give me a condition number. At 6, now I have met the minimum criteria, but it's yellow, it's not great. And now as I continue to add some, my reference condition number is actually getting a little bit worse as I added that last one. So you can kind of play around in here and say, what if which of these do I really need to get the condition number that I'm looking for? Okay, so again, I haven't taken any data. This is all just a geometric relationship that I'm getting interfacing with the CAD model and the high degree of accuracy I can get from that model. In addition, or sort of behind the scenes, I can come over here to edit, and I'm gonna go ahead and delete a couple of these just to simplify my display. Okay, so I've got a couple forces, I've got some responses. Behind the scenes, if I go over to edit, it's just a good old-fashioned test lab geometry. Okay, it's just a point out in space with a component name, a number, an XYZ location, and then Euler angles. All done. Obviously, 4 decimal places of accuracy is beyond anything I can do by hand. But you notice, so if I look just at, let's see, what are the, if I want to compare this guy, which is number 5, he's pointed in, and this guy, which is number 6, these guys are oriented different, right? This guy's on the negative Z face, this guy's on the plus X face. So I look at points 5 and 6 in here. There's 5 and there's 6, okay? And you see the Euler angles for those 2 points. Make this a little bit bigger. The Euler angles are automatically accounting for that rotation of that transducer. Okay, so red, green, blue straight up, red is straight up, green and blue is out this way. That is because I put those transducers on the structure differently. So now as long as I mount that accelerometer on my actual structure, oriented the way I show it in the CAD virtual instrumentation window, my Euler angles will be correct and very, very accurate. And so my displacement shapes, my ODS shapes or my mode shapes will all be the correct phase because I'm graphically aligning those transducers as opposed to just saying, oh, just put them on, and the person mounting the accelerometer decides, well, it's easier if I have the cable coming out this side. If you just laid out points in space and you haven't put a transducer on there with a specific orientation, they might do it differently than you expect them to, and then you've got the old rolled accelerometer problem where you have phasing issues and the directions are wrong. This virtual instrumentation is alleviating all of that kind of error-prone stuff. In addition, let me just show you what if I do, and this will be on here. But what if I don't have CAD model and I've got this structure and I've only got it for the day and I want to use some of the features of virtual instrumentation? Now, we only support the PRT and JT formats, but you can use something like this free app, which is called Scaniverse, which is a LiDAR scanner that you can get for your iPhone. I don't know if there's an Android counterpart, but for your iPhone, you can download Scaniverse and it will use the LiDAR face recognition technology to actually create a 3D model of your structure. And this is obviously not going to be as refined as getting a CAD model, but if you don't have anything, I'll show you what this kind of thing looks like. If you don't have anything and you want to use a solid model, you can bring in something like this. So this is the tire. I'm going to delete all of these components just to get them out of the way. And so here is a scan of the actual tire that we had in test. Now you notice this is a little bit different layout than the CAD model, right? So this, maybe we're testing a new generation of hardware and the spokes are a little bit wider. There's a different number of bolt holes, etc. So this is a Scaniverse LiDAR scan. You can see it's a little bit cruder, but the size, the layout, the orientation of the structure is all accurate. And I can still I still have the ability to place transducers on there and it will follow the orthogonality of that surface. So again, still way more accurate than doing anything by hand in terms of measurement or just eyeballing it. That ability is there. In this case, Scaniverse outputs an STL model. I had to use NX to translate that STL model into a CAD model, but it can be done. These are pretty nice workarounds. And just to show you how this would work, I'm going to bring in Neo impact testing here. So this is impact testing in Neo, and I want to utilize some of these features of the virtual CAD display, virtual instrumentation, to help me set up my impact test. So if I start impact testing in Neo, this is where I'll end up. I see my typical channel setup like I would in any other test. If I go over here to geometry, I have already loaded in this little motor and transmission here and laid out some transducers. And so I've got all this work already done. It's time to start instrumenting this test. I set this up a couple weeks ago before I had the part, and this tells me exactly what I want to do. So if I go back to instrumentation here, I can now say geometry lookup. Okay, and that's going to import or bring over this CAD display that I have. And so now I can use this display to say, okay, I'm going to plug in these transducers. Here's my force reference. There, it selects the correct transducer. It knows where it is or what type of transducer it is, and I'm going to assign that to a channel. So it knows it's at engine 1. It's in the negative Z direction. It knows it's a force. It knows it's a force, and I just can't get it to show you that right now. But now I'm going to start doing my responses. So I select this accelerometer. That's going to be plugged into channels 2, 3, and 4, and I assign that. And it brings it over, has the correct component and node number. Again, I've got room for one more triax. You might think it'd be this guy, but really I'm gonna do this guy. Again, graphically, visually, I can see which one I'm grabbing. and it just helps to error-proof this process a little bit. When I planned, I might have thought, oh, it's obvious that I'll go from this one to this one to this one to this one. If I want to measure these two channels at the same time, maybe to help distribute the mass loading effects or something, again, I can graphically, visually see that intention laid out right here and make sure that I'm hooking up my transducers correctly. So again, it's about error proofing, it's about speeding up this process and making it more accurate. So that's all I have. That's a crash course through the new CAD display. Again, it's a zero cost license. If you're running 2306 or higher and you want to give it a try, go ahead and call support and we'll get you that $0 license and you can start playing with this.